we have one more thing to do about normal operators. And the statement is that phi, and this is a map from V to V. This is it's got inner product, Hermitian inner product. So this is a map of complex vector spaces. This is normal. And remember that what that means that phi star equals phi star phi. So it commutes with its adjoint. And it's normal if and only if, here's the condition, if the lengths, the way phi changes lengths is exactly the same way that phi star changes lengths. And that's for all x. Okay, so the way, again, that phi changes lengths is the same as the way that phi star changes lengths. So the proof, let's do this direction. So it's saying, assuming that it's normal, we need to show that it fixes that it does the same thing, that phi and phi star do the same thing to the lengths. So then what is phi x squared? What is the square length? Well, that's just phi x paired with phi x, right? But because this is an adjoint, we can now say that that's the same thing as phi star phi x paired with x, right? But now phi star and phi commute. So that's going to be the same thing as phi star x paired with x, which is the same thing now moving that phi back over. It's going to be phi star x paired with phi star x, which is the length squared of phi star x. It's really very simple. That direction is. The other direction is, I'm going to skip most of this proof because it's a computation that you can do for yourself. But what you want to do is you want to compare. You want to do the same thing as this, but basically in reverse. You want to compare. Phi star phi of x paired with y. What's that? That's the same thing as phi x phi y. But you want to know that that phi star phi is the same as phi star, right? So if I look at phi star phi applied to x and then look at it paired with all y, then that's enough to characterize what phi star phi is. Yeah. So if you think of the y's be running through an orthonormal basis, that's going to give you the coordinates of phi star phi of x in that orthonormal basis. So now I want to do the same thing with phi star, right? So compare that to phi star x paired with y, which, as we've seen over there, this is again the same argument over here. That's phi star x, phi star y. And the point is that you're going to express the inner product in terms of the norm. And that's something that we've seen so many times at this point that I'm not going to go through it again. But the idea is that if you know things about norms, then you can recover things about the inner product. And that recovering things about the inner product is enough to know that phi star is the same thing as phi star is the same thing as phi star. Okay. This is a nice characterization. So now let's move on. Are there any questions about normal operators? Okay. Let's talk about positive semi-definite matrices and singular values. Okay, so the setup is that we have a vector space V. Let's fix V with an inner product, Hermitian inner product, and there's will tell you what it's a vector space over. The dimension over the complex numbers of V is n. So it's a finite dimensional complex vector space with a Hermitian inner product. So we have a C linear, so a complex linear homomorphism, V from V to V. It's an endomorphism of V, and that's called self-adjoint. I think you've already seen this term. I may have even already defined it on the board. It just means that phi equals V star. In particular, this is normal. Y is normal. Sorry, why is self-adjoint? Why is the self-adjoint operator normal?
It clearly commutes with its adjoint.
Yeah, it's just like, you know, when you multiply it by itself, you get it square, and it doesn't matter whether you multiplied it by itself and then itself, or itself and then itself. It's like, it commutes with itself, sort of so tautologically that it looks like nothing is happening, which it isn't. And is further, so if you have a self-adjoint operator, then I'm going to call it positive semi-definite. That's if Px paired with x is greater than or equal to 0 for all x in V. And I will call it positive, cross out the semi, and then I'm going to just write a greater than. Yeah, so it's positive definite if these inner products are all strictly positive, and not just greater than or equal to 0, but strictly positive. Okay, give me an example of a positive, so give me an example of a positive semi-definite matrix or operator. How can you arrange that the inner product of x with, sorry, phi of x with x is always greater than or equal to 0? The identity certainly does that. More generally, the identity?
Any matrix with positive entries on the diagonal?
Yeah, so diagonal with entries that are greater than or equal to 0, right? How do you do positive definite? Just make that into a greater than? Yeah. Okay, and it turns out that that's sort of all there is up to similarity. So let's state a theorem here. So the theorem is that let phi be self-adjoint. Nice that there's a short way to write that. Then phi is greater than or equal to 0 if and only if all eigenvalues are non-negative. That is, if you assume that the thing is already self-adjoint, then the only thing you need is that all the eigenvalues are greater than or equal to 0. Now, we proved things about self-adjoint operators, right? They're all diagonalizable with real eigenvalues, right? This is what the spectral theorem says. You can always diagonalize a self-adjoint operator. So the only extra condition we're putting, sorry, not only can you always diagonalize it, but when you do diagonalize it, the diagonal entries are always real at that point. The only additional condition we're putting is that the entries in the diagonalization, they're all greater than or equal to 0. That's all we're saying. And the same thing is true if I put, greater than there. Right? That's all we're saying. So the proof is very short. So the proof, you just pick orthonormal basis V so that the matrix of phi in the basis V is diagonal And then, so that B in this basis B is greater than or equal to 0 if and only if this stuff. Right? And that's all there is, it's really just that. Yeah, so the point is that self-adjoint operators, you can always diagonalize them by choosing an orthonormal basis. And then once you do that, all the eigenvalues are real. Then the only further condition is that the entries have to be greater than or equal to 0. So let's say non-negative or positive. I'm going to say it, right? It's the greater than or equal to 0 is non-negative. The red one is positive. Yeah, keep in mind that picking an orthonormal basis B hasn't done anything to the linear transformation of B, right? It's just choosing to express it in certain coordinates. So it's not changing anything about phi to pick a basis. It's just saying that if you pick your basis judiciously, then it's very easy to tell whether or not your operator is positive semi-definite. That's the point. Okay, so corollary. You have a matrix A, which is equal to its adjoint, then that's positive semi-definite. That means that there exists a unique matrix B, also positive semi-definite, with B squared is equal to A. That says that this matrix has a square root. Now this will be familiar to some of you from the midterm. This is only for positive. I mean, the statement that we're making is for positive self-adjoint operators that are positive semi-definite, as we've written here, and it says that there's a square root that's also positive semi-definite. And we define, so not that I have to tell you this, but we define that B is the square root of A. Why is it a unique square root? What about the definition makes it unique instead of like being like plus or minus?
We need it to be positive.
Yeah, so I told you it had to be non-negative, right? And that forces you to choose the positive sign. So we say that B is the square root of A, and proof. So there's two parts. There's existence. So the existence says that A is U, B, U star, with D being diagonal. That means that the square root of A, and it is the square root of A, is U times the square root of the diagonal one times U star. It's really very, once you've diagonalized it, the point is that it's very easy to take the square root of a diagonal matrix. You have assuming the diagonal matrix has positive entries or non-negative entries. Right? You can take the square root of a diagonal matrix with non-negative entries by just taking the square roots of the diagonal entries, which you can do and get real things, right? You have to get real things, and the reason why you can do that is because they're greater than or equal to 0. Uniqueness. I'm going to leave this as an exercise. It's not a sign or anything, but it's one of those things that you can just check yourself that's unique. Okay. Let's see. Here's a proposition. It says that if A is positive definite, not positive semi-definite, but positive definite, then if I take nu of x to be the square root of, let's see, now it's x star A x, I claim that that is a norm. Think about what happens when A is the identity matrix. What you're doing is you're taking just x star x in that case. And what you're doing in here is sort of after change of basis, what you're doing is you're taking sort of remember this is true, this is supposed to be for all x. So if you replaced A with the conjugate of A, it wouldn't change what this norm looks like. So in the new basis, then what you'd be doing is you'd be taking like the sum of the squares of the entries of x, but weighted according to the diagonal entries. That's kind of what you're doing here. It's like a weighted norm. You're just sort of stretching the various coordinates in that orthonormal basis. you're stretching them by factors that come from these diagonal entries. So instead of the unit sphere being a sphere, what it's going to be is some sort of ellipsoid-like shape, right? Because you've stretched some of the axes. Actually, you've set some of them to, well, this is greater than 0, so none of the entries can be 0. So it actually is stretching all of them by some positive amount. It might be shrinking them, but it's still stretching them by a positive amount and not a 0 amount. The proof uses one of your homework exercises. So what is this? This is nu of x is really, is the norm of a to the 1/2, so the square root of a, if you like, x, and then you can take this in the 2 norm. So remember what I said, you're just really rescaling the 2 norm. So let's make that explicit. Let's say you're going to rescale, and then you're going to apply the 2 norm. That's exactly what this is doing. And what is that? Well, so now let's apply. So in homework 2, number 3, problem 3, what you said is that if you had a linear map between vector spaces and a norm, then you could pull back the norm. So the point is that let's take nu, that's going to be mu composed with phi for the norm mu, which is going to be the usual 2 norm, and a, sorry, phi being a to the 1/2. Right? What it says is that if mu is a norm and phi is an injective linear map, then the composite is still a norm. Yeah. So what we're doing is we're taking x to a to the 1/2 x, and then we're applying this usual norm that we know is a norm. And the point is that since a to the 1/2 is injective, why is it injective? It's because it's positive definite, right? So this is greater than 0. So all the eigenvalues are positive, none of them are 0. So the kernel is 0. Remember, an eigenvalue of 0 is the same thing as saying that there's a non-zero kernel. Right? An eigenvector with eigenvalue 0 is the same thing as a kernel element. Agreed? Yeah. So this condition implies that the map given by A is injective. So we can apply this homework exercise, and it just immediately tells you that the composite of the standard norm with the injection given by a to the 1/2 is a norm. You guys remember this homework exercise? Yeah, good. I like this lecture, this particular lecture, this topic that we're doing today, because it explains, finally, after a semester and a half, what every linear transformation looks like. I know it looks like we're only doing positive definite matrices right now, but by the end of today's lecture, you're going to see what every linear transformation looks like. And they all look ridiculously simple. Your reaction is going to be, why didn't you just tell me that on day 1 that all linear transformations look like that? And so what the goal is to understand things in terms of these positive definite ones, which I hope you'll agree, since they're all up to change of basis, just diagonal with non-negative entries like this, these are pretty simple to understand. Right? Now there's a choice of basis that goes here. So you have to look at where your orthonormal basis is, but up to that, it's really simple. So let's describe everything in terms of those. So definition. A is C to the n by n. So this is just an arbitrary n by n matrix with complex, so m by n. M by n matrix with complex entries. And it has modulus. We're going to write it as the absolute value of A, and it's going to be the square root of A star A. And note that this is, again, a non-negative, a positive semi-definite matrix. Well, why is that a positive semi-definite matrix? Let's just check. Right? It needs a couple things, right? We need A star A to be positive semi-definite to begin with, right? So we need it to be self-adjoint, and we need its eigenvalues to be non-negative. So we have to check that. So this actually needs 2 things. It needs that A star A we need it to be self-adjoint, right? So what's the adjoint of A star A? You've done this computation so many times at this point, right? You have to reverse the order and take the adjoint of each, but when you do that, it's just A star A again. It's all right, it is A star star. This is A star A, right? Okay, good. That's nice. So it's a self-adjoint. It also needs that when we take A star A and we take a vector X, when we pair it with X, why is that greater than or equal to 0? Remember, the whole point of having the adjoint over here is that you can move it over to the other side and remove the star, right? So what is that? That's just AX paired with AX. That's good, because that's the square length of AX, which is greater than or equal to 0. Right? Very easy to check these things. Sort of kind of ridiculously easy to check these things. Oh, I mean, maybe you don't learn very much by checking it, but at least you see that it's true. So proposition. And this is kind of the key to everything. It's that the norm of the modulus times x squared. Now I know that there's a lot of lines in this thing. Just be glad that A isn't a capital C. This is just kind of a fun little thing, but what would happen if you took this thing? That's a true statement. Right, what it says is that the norm of C divided by the norm of C equals 1. Anyway. Yeah, notation can get pretty bad sometimes. So the norm of the modulus of A times X is equal to the norm of AX for all X. In I'm going to make that C into an F. Yeah, so remember F is going to be R or C. And if at any point you need it to be C for the statement to make sense, then just take it to be the complex numbers. So I'm just going to write, in my notes I had for all X and F here. So maybe the right thing. Oh, I see the setup. I see the setup that I had was always C linear. But anyway, things work over the reals if everything is real. In that case, the star is just the transpose and so on. Okay. In F to the n. Sorry. Remember F to the m. So this is an m by n matrix, right? So AX is an element in F to the m. Yes.
Is that true for any norm? Or is it a particular choice?
This is the norm. Yeah. So if you see a norm without having been specified,
So the Euclidean.
it's the Euclidean norm. Yes. So if I'm writing a matrix and I put a norm around it, then I mean the standard, not a matrix, but if I'm writing F to the n, and I write a norm of something in F to the n without further comment, it's the standard one. Yeah, otherwise I would have to say for any norm and so on and so forth. Yeah, I'm looking at the standard one. Good question. Okay, so proof. What is the square length of AX? Sorry, modulus of A times X. Well, that's modulus of A times X, modulus of A times X. That equals, so the standard sort of thing to do, right? You take the star of this one and put it on the other side. Modulus of A star, modulus of A X, X. But what can you tell me about modulus of A star times the modulus of A? What's the modulus of A star? Let's see, now how do we define these things? There it is. The modulus is this thing, and here's the key point. It's greater than or equal to 0. That means that it is self-adjoint and positive semi-definite, but self-adjoint to begin with. So this is modulus of a squared x. What is the modulus of a squared? Just happened there. Yeah, so modulus, well, that's right, yeah, this is because it's Hermitian. What is the modulus of a squared? It's a star a, right? So this is a star a, x, which is ax, which is the square length of ax. Right, simple calculation. Okay. So what does this mean? So what this means, I swear there's geometry that's going to come here shortly, and it's going to come from this actually, that the kernel of A is equal to the kernel of the modulus of A, and that is the image of the modulus of A. So there's we will see that this is going to be geometric at a certain point. What this says is if you replace A with the modulus of A, you don't change the kernel, right? And what happens is the kernel of A is orthogonal to the image of the modulus of A. So there's some nice geometry there, right? The image of the modulus is orthogonal to the kernel of the modulus, but also orthogonal to the kernel of A itself. This is nice. Proof is really very short. So this equality over here, so equality sub 1, so that's equality sub 1, that's equality sub 2. Yeah, so equality sub 1 is that, well, what does it mean to be in the kernel? I said this just a few minutes ago. Right? To be in the kernel means you're an eigenvector with eigenvalue 0. Yeah? So the point where, it means that even better, it means that the length of A times U is 0, right? Say you're in the kernel means that the length of A times U is 0. So this is just the length of AX equals 0 if and only if the length of modulus of A times X equals 0. That's really all it's saying, right? This is the special case of this statement where the lengths these two lengths are both 0. Now, let's see. How about equality sub 2? Why is that true? Well, forget about the fact that this is the modulus of some matrix, which has additional properties. The kernel of any linear operator T is the image of T star per. So I claim that this is actually the simplest thing. It comes down to 221 stuff. And when I say it comes down to, I mean, as soon as I write down what I'm about to write down, it'll be like, oh, right, yeah, okay. So here's the idea. If your matrix for T looks like this, and you ask what it means for T times this vector to be 0, it's the same thing as saying that this vector lies is orthogonal to all of the rows, right? So this matrix is viewed as a bunch of columns, if you like. Actually, it's viewed as a bunch of rows, whatever. It's viewed as a matrix. It's a linear map that goes this way, right? What is the image of T star? The image of T star is the row space. Yeah, that's all. It's like, yeah. Of the complex conjugate, by the way. Remember, T star is the map that goes, it's the map that takes a row vector here to a row vector here, but you have to take the complex conjugates of the rows in order to do that, in order to put the star on. Yeah, so you could think of as the conjugate transpose as taking the transpose and then taking the conjugate and then using column vectors the whole time. Or you could think of taking the same matrix, just taking the complex conjugate and then using row vectors instead of column vectors. Yeah. So the point again, it's just very simply that this matrix times this column is 0 if and only if this column lies in the orthogonal space to the complex conjugate row space. And now the point is that also the modulus of A star is the modulus of A. Okay, so what does the corollary actually mean? So the corollary means that first of all, that the modulus of A is orthogonal projection followed by, well, I'm not sure exactly what it's followed by, but the point is that it's going to be followed by something, right? So the kernel of the modulus is orthogonal to the image of the modulus, right? When the kernel is orthogonal to the image, that means that what you're doing is you're doing an orthogonal projection modulo the kernel, and then the image is going to be orthogonal. You can then do something to that image, right? I'm not telling you that this modulus is actually orthogonal projection. It's orthogonal projection followed by, well, something. And we'll figure out what shortly. But this is just a statement, again, that the kernel is orthogonal to that the image is orthogonal to the kernel. Yeah? Okay, and what else do we know? We know that the image of, of A maps into, by the modulus, into the kernel of A. Perfect. This is by the universal property of quotients, right? So what can you tell me about the modulus of A? The modulus of A, whatever it is, it's some linear transformation, and it has the property that it vanishes on the kernel of A, because the kernel of A is equal to the kernel of the modulus of A. That means that the modulus of A induces a map from the image of A into the image of the modulus of A. That's what this is saying, right? Sorry, into the perp. Yeah, so this is by the universal property. Again, it's because this map over here, the modulus of A, vanishes on the kernel of A. That means it induces a map from the image of A into something. The image of A being isomorphic canonically to A modulo the kernel. That's the V modulo the kernel. Okay. So the point here is that the modulus of A, this is 0 on the kernel of A, first of all, and second of all, that the kernel of A perp is equal to the image of the modulus of A. That's just the, look at this statement over here. So I've just taken the perp of this one and the perp of that one. Okay, so the modulus of A has non-negative eigenvalues, and so I want to give those things names. These can be called the singular values of A are the eigenvalues of the modulus of A. Then that's the same thing as saying, i.e. root lambda 1 up through root lambda n where A star A has eigenvalues lambda 1 up through lambda n. Okay, these are called the singular values. What I want to do is I want to now get to the point where I can draw an example to show all of this stuff. Well, this is just going to be a matter of setting up some notation. And so it's just going to give you standard notation for all the objects that are sitting around here. So here are some running assumptions. Okay, so I have a map of vector spaces. This is going to be a homomorphism of permission spaces. Permission vector spaces over F. That means that they come with permission forms, and that the linear map takes one to the other. Okay. Note that you don't have to choose a basis beforehand. You just have to have a permission form. Okay, let's see now. The singular values, remember, are the eigenvalues of the modulus. The singular values are going to be sigma 1 up through sigma r, and then sigma r plus 1 up through sigma n. These things, the singular values of A, remember these are eigenvalues of the modulus, and I want these things to be the ones that are actually not equal to 0. I want these ones to be the ones that are 0. Tell me, what is R in this case?
The rank.
That's the rank. Right, so R here, that's the rank of A. Right? Because, again, the kernel of A is the same thing as the kernel of the modulus of A. So the rank of A is just the number of non-zero eigenvalues of the modulus of A. Or if you like, the dimension of the kernel is the number of 0 eigenvalues of the modulus of A. So the rank is n minus that. Okay. And I'm going to choose V1 through Vn. That's going to be orthonormal basis of the space X, so that the modulus of A scales to VI by sigma I. That is, VI is an eigenvector with eigenvalue sigma I. An eigenvector of the modulus. So this means in particular that V R plus 1 up through Vn, that's a basis for the kernel of the modulus. Sorry, the kernel of A, in fact, because the modulus of A and A have the same kernel. That's what the corollary says. The same thing. Okay, so let's talk about the geometry of the modulus of A. We've already mentioned it a couple times, but let's say it now in a little bit more detail with notation. So what we're going to do is we're going to kill the kernel of A, right? So you're going to start with your vector space, and inside there's going to be some subspace that's going to be the kernel of A. And what you're going to do is you're going to flatten that into a point, right? You're just going to step on the kernel. You're actually going to flatten it in a orthogonal kind of way. So you're going to orthogonally project away the kernel. And then what you're going to do is kill the kernel of A and rescale V1 up through VR by positive sigma 1, by positive sigma 1 up through sigma 1. Okay, that I hope you understand is a very simple thing to do, right? You're going to do an orthogonal projection that's going to kill the kernel of A, not just the kernel of the modulus of A, but killing the kernel of A. Those are the same subspace, so that's not so bad. You do an orthogonal projection, because remember, V1 up through Vn, that's an orthonormal basis. So what you're doing is you're going to kill the last bunch of these things, and then you're going to rescale the other ones by positive constants. This is a simple thing to do. We can draw a picture, which I will do in just a second, as soon as I define polar decomposition. Here. This is decomposition. What it says is that if you have A in F n by n, then A is equal to a unitary matrix times the modulus of A for some U O n of F. So it's unitary if it's the complex numbers, and it's orthogonal if it's the real numbers. So what does that say? Remember, we know what we're saying we know what the modulus of A does. It does something really nice. There's a basis in which what it does is it projects away, orthogonally projects away the last bunch of basis vectors, and then it rescales the other ones by positive scalars. What we're saying is that so that's what the modulus of A does. That's a really simple thing to do. There's an orthonormal basis where you kill some of them, and then the other ones you just rescale. What's the difference between that and A? The difference between that and A is that you multiply by a unitary matrix. So what it's saying is you're going to do the modulus of A, and then you're just going to rotate. That's it. So remember when I said it's followed by something? That something is this U. That's actually not, this is modulus of A, it should say A, but the point is that that's what the something is telling you. There's a rotation that's going on. Well, the something, I see, now the something here, technically this something is this, is the rescaled, right? So that this is the modulus of A. Modulus of A is orthogonal projection followed by something, and that something is the rescaling of the other basis vectors by some positive scalars. I could erase I could erase the bars around the A, and then I have the something, and then that something is that U. That's the only difference, right? So modulus of A kills some basis vectors and then rescales the others. A further then rotates those basis vectors in an orthogonal kind of way. It preserves the orthogonality when you rotate. That's the idea. So what does this feel like? By the way, what does this feel like? If I had written in the one-by-one case, in the one-by-one case, what I have is like Z is a complex number. And what can you tell me about Z? This implies that Z is equal to, Z is going to be equal to E to the I theta times the modulus of Z. This is literally the polar decomposition of a complex number, right? It's saying that there's going to be some real thing, which is this one, and then you're going to take this real one and you're going to multiply by then you're going to rotate it. And so this is a polar decomposition of any complex number, and the point is that any matrix has the same kind of decomposition. And this is U is unique. This U there is unique if A happens to be invertible. If A is invertible, then it's this unitary matrix is unique. Yeah? Let's do a big example. So our example is going to be a real matrix because I want you to actually be able to see it. Here we go. Minus 2, 1, and then bear with me on this. It's going to be 1/5 times 4 minus root 6, and 1/5 times minus 2 minus 2 root 6. That's our matrix A. I apologize for there being all the irrational entries, but if you want things to work out nicely, either A or its modulus has to be ugly. I don't know of an example, and maybe you can construct one. That would be really nice. If you can, please tell me, and I'll use it in the future, of an example where both A and its modulus are pretty. I don't know how to do that. Okay, so what is this matrix? Just so you know, this is approximately equal to, well, we know what minus 2,1 is approximately equal to. This is 0.31 and negative 1.38. That's what this is approximately equal to. So I can tell you what multiplication by this matrix does, right? So multiplication by this matrix, it takes this. So if this is the first standard basis vector, and that's the second standard basis vector, then when I map multiplication by A, where do these things go? This is 221, very basic 221. They go to the columns of this matrix. So the first standard basis vector goes to this minus 2,1. Right, so now if I put the, well, I'll just draw that one in white. So it goes to minus 2, comma 1. Let's make sure that these things are pretty close to that, like this. Yeah? So that's the first one. And then there's the second one, which I can highlight in yellow. Those of you online might not be able to see it. It doesn't really matter. There you go. And that goes to something that's approximately 0.31 and then minus 1.38. So that's going to be something like this. And then maybe down here it's less than 2. It's about 1 1/3. So it's about like this. That's fair enough? That's what the linear transformation does. We want to try to describe this in terms of orthogonal projections and rotations and scalings. Right? We're going to look at orthogonal projections, rotations, and scalings. So what is A star A? Do you want me to actually do this computation or just tell you what the answer is?
Just tell us.
Because doing it's not that hard. It's just multiplying a bunch of things with square roots and things cancel. I did spend a lot of time making sure I got this exactly right. It's in the details are in the notes if you want to see them. But here we go. This is going to be 5 minus 2 minus 2, 2. See, that's the one that looks pretty. Right? Okay. Okay, so then, again, you can actually check this. Just literally multiply this matrix by its, well, conjugate transpose is just transpose here, right? Because everything's real. Don't be fooled by the square roots. They're still real. They're not square roots of negative numbers. They're square roots of positive numbers. Okay, what's the characteristic polynomial here? Remember, we're supposed to be finding the eigenvalues, right? So this matrix, I claim, is positive definite. Well, okay, it's positive semi-definite. As it turns out, it is positive definite. How do you know, without doing any computation, that this matrix is positive definite? Look at the pictures on the board. Ben is going like this. Yeah, so what about it, Ben? How do you know?
Just because, well, you can just look at the columns of the matrix too. They're not like multiple of each other. There's only 2 columns.
Yes, you're saying that the matrix is invertible, right? So like this picture tells you that the span has dimension 2, right? These 2 vectors are linearly independent. And therefore, this matrix has 2 non-zero eigenvalues. Okay, so what are they? Well, you have to calculate the characteristic polynomial, right? So let's see, where am I on the page? I'm over there. So P A star A of T is going to be, well, it's going to be 5 minus T times 2 minus T. Minus 4. Agreed? What's that? going to be t squared, let's see, minus 2 minus 7t, and then let's see now, plus 10 minus 4 plus 6. And what's that? Yeah, t minus 6 times t minus 1. Okay, so that means that what are the singular values? Remember, this is a star a already, right? The singular values are the square roots of these things. Alas, I did not make the eigenvalues squares again. Only I do what I can do, but okay. What are eigenvectors? I say the eigenvectors, you get choices. We want to choose unit eigenvectors for these eigenvalues. This one's the easier one, right? How do you get this one? You subtract 1 from the main diagonal, and then you take any column you want, right? Because you have to make a unit vector, but we're looking for the, yeah, because it's supposed to be an eigenvalue with it's an eigenvector with eigenvalue 1, right? So let's see now. So if we do all this, what do we do? We're going to take, this thing minus the identity is going to be a 4 and a 1. We're going to get a minus 2, 1 there. Yeah? Now that doesn't work. Oh, I see. We need to take the kernel. So for this one, we're going to take the kernel of the matrix. It is 4, 1, minus 2, minus 2. What's the kernel of that?
1, 2.
Right? You're going to take 1 times this one plus 2 times that one. So that's going to be 1, 2. There we go. Okay, so we can draw that. Yeah, so I'm going to draw my big picture over here. All right, so we're going to take 1, comma, 2. There it is. And let's draw that one in, red. Okay. Okay. So that's going to be, oh, wait a minute. Oh, no, did I get this wrong again? V2. Oh, that is 2. Right, that's V2. Good. No, I got it right. So this is V2. Right, this is the second one. The first one, okay, without doing any more computation, what's the first one?
-2, 1.
It's going to be -2, 1, because we know it has to be orthogonal to this one. Yeah, so it's going to be -2, 1, right? And those things are orthogonal. That's V1. Now, actually, I want you to now ignore the tick marks because I want these to be unit vectors. So I'm going to draw now the unit circle here. All right, so the unit circle is going to look like that. Okay, that's my unit circle. So that's going to be length equals 1. Yeah, so again, ignore the tick mark. It's actually going to be this thing. It's going to be 1, 2. It's going to be 1 over root 5 times 1, 2. And this is, it's going to be 1 over root 5 times -2, 1. Agreed? Okay. Now, what is A V1? When you apply A to V1, what you get is, well, some big mess involving square roots of 6. And I'm just going to tell you what the answer is. So A V1 is going to be, it's going to be 1 over 5 root 5 times, it's going to be 24 minus the square root of 6, minus 12 minus 2 root 6. which is approximately equal to about 1.93 and negative 1.5. Okay, where is that? That's going to be, let's see now, that's going to be about over, let's see now, 1.93 is nearly 2. So if that's 1 now, remember, this is now, that's now 1. That's now 1, right? So 1.93 is nearly 2. And then we're going to go down about 1.5, no, about 1.5. So there's 1.5, maybe over here. Oh, it's not that thing. It points slightly further down than that. Draw it like this. Okay, so this is not the same line as that one. Okay, the blue one is not the same line. So this is going to be A, V1. Then what's AV2? AV2 is going to be, let's see now, that's going to be 1 over 5 root 5 times minus 2 root 6, and then 1 minus 4 root 6. And that is approximately equal to, just so we can draw it, that's the reason why I'm writing these things down. This is minus 0.62 and minus 0.79. So that is going to be, as it turns out, orthogonal to this one. So let's see now, if that one looks a little bit pointed that way. So good. So like this. Go, and that's A, B2. For this is orthogonal. Okay.
And that still has length 1.
Say it again.
Does that still have length?
And it does still have length 1. I want you to check that. I was actually going to write this. So the length of AV1, that is root 6. So that's going to be root 6. The length of AV2, that is going to be 1. What is that? That root 6, that is going to be, that's the length of sigma 1, V1. And that's the length of sigma 2, V2. Right? So really what we're doing is we're doing this. That's going to be sigma 1, V1. And that is sigma 2, V2. Right, remember what the modulus of A does. What the modulus of A does is it scales, so there's no projection because there's no kernel. So what it does, it's going to scale one of these basis vectors by root 6, and it's going to scale the other one by 1. Right? What does A do? It does the same thing, except you have to rotate after. So you take this V1, so you take this V1 and this V2, and what you're going to do is you're going to rotate, you're going to scale them, right? You're going to scale them, that's what this does, and you are then going to multiply by U, which does the rotation here, right? So again, A does the blue stuff, and modulus of A does the red stuff. And the difference between the modulus of A, remember the modulus of A is doing something really, really, really easy here. It's choosing a basis, that's the basis V1 and V2, it's an orthonormal basis, in which all it does is scale them, right? And what we're saying is that what A does is it just follows that by rotation. That's it. That's what the polar decomposition theorem says. I hope this makes it clear geometrically what's going on, right? The point is that the modulus of A does something that's really simple. It says, choose an orthonormal basis in which things look so pretty that all you're doing is multiplying them by scalars. They're all eigenvectors, right? Now, that modulus of A, it's not quote unquote related to A in any way, right? You know, your matrix A needn't have eigenvectors. It needn't even have real eigenvectors. It needn't have real eigenvalues if you have a real matrix. But nonetheless, there is an underlying real matrix, which is the modulus of A, that when you do a rotation afterward, that gives you A. And it's the rotation part that gives you the non-real eigenvalues, if you have non-real eigenvalues, right? Here's where the non-real eigenvalues are coming from. But here, they're just sort of, you're multiplying by positive scalars. So you can choose this orthonormal basis. There's V1, there's V2. So that all modulus of A does is rescale those by the singular values. There they are. Right, there's sigma 1, there's sigma 2. You're just rescaling by those singular values, and then you have to follow it by U, which I'm now going to change the color of this to make it blue, because otherwise the board's going to look pretty nice. Okay? Be clear what the polar decomposition theorem says.
Could U involve a reflection?
U can have a reflection in it, yes, because U is just, it's in ON, it's not SON. So yes, you can have a reflection in it as well. And in fact, the first time I wrote down this example, I thought it had a reflection. I really wished it had, but it didn't. But at a certain point, yeah?
So the proof of the polar decomposition theorem is just the proposition that we proved earlier that modulo AX and AX are isometric.
More or less, yes, that's right. We're going to write down singular value decomposition, which you'll see is basically just that. It's because it's preserved. Yes, it's basically that. I would like to actually write down, I wanted to draw one more thing on this picture. And that is that, see this circle, which I should now draw in red? It gets taken to this ellipse. Oh, sorry, that circle I wanted to be white. I'm going to erase it and redraw it. That's not what I wanted to be red. What I wanted to be red was the ellipse. Here, let's redraw this. Okay, and there's this ellipse over here. So the rescaling takes this circle to this. It's hard to do this. It's hard to do this especially because there's another one here, which is going to be this one, right? Which now looks like this. And this one is rotated that way, so it touches slightly earlier, and then goes around like this. Something like that. Right? Yeah.
I have a question. So if there were a kernel, right?
Yes.
It would just be everything, like, say you were in 3 dimensions and there was kernel dimension 1, it would just be going down a dimension to like this example.
Yes, that's right. There would be a third basis vector, which would be orthogonal to these two. And by the way, it wouldn't necessarily be, the third standard basis vector. There would just be some choice of coordinates where you'd have a plane essentially, and there'd be an orthogonal vector which A kills and modulus of A kills, right? And then modulus of A, the point is that it then multiplies these two by scalars. Yeah. Okay, so let's say what Schmidt decomposition does, and then we'll maybe do the singular value decomposition next time, which is the same thing really. So again, this tells you what all linear transformations look like, right? In some sense, they're all just, you pick an orthonormal basis, you kill some of them, you rescale others, and then you rotate. And your reaction should be, well, why didn't you just say so? Yeah, so I don't know why you didn't say so, to be honest. So, no. I guess we wanted to have some mystery. So if I take WK, to be 1 over sigma k times A VK, then I claim that W1 WR is orthonormal capital Y, which remember is the target of our linear transformation. Where are these vectors? That's these things. Oh, nope. It's these things. It's going to be 1 over sigma times the AVs. That's this one. This one. Yeah. And we already know that by looking at the picture, right? So the proof is going to be similarly simple. It's just a little check. So the proof is that if I take sigma I, Wi, and pair it with sigma j, Wj, what am I supposed to get? I'm supposed to get 0 unless I equals j. And when I equals j, I'm supposed to get sigma I squared. That's what I'm supposed to get, right? Because the W is just supposed to be orthonormal. So if I multiply them by scalars, then the scalar is supposed to come out and you're supposed to get 1 from the Wi. Okay, but what is it actually? It's A Vi paired with A Vj. This is just by definition. And what's that? That's going to be A star A Vi Vj. And that is, remember what the V's are. We fixed an orthonormal basis for the modulus of A. That's what the V's were. So this is going to be now sigma I squared Vi Vj. And that's sigma I squared Vi Vj, which is just sigma I squared times the delta Ij that we wanted. I.e., this is sigma I squared if I equals j and it's 0 otherwise. As I said, it's a simple calculation. So then we see a theorem. A has what's called a Schmidt decomposition. And that's going to be A is equal to a sum from K equals 1 to R, sigma K, WK, VK star. And so here VK star, you should think of these if you want as matrices. So the W's are columns, the VK stars, those are rows. And you're literally just taking scalars times column times rows. So these matrices have size m times n, right? That they are what you think. So VK star, what is that? That's going to take x, and it's going to map it to x paired with VK. So what this says, so the coefficient on WK in AX is supposed to be sigma K times x paired with VK. That's what this means. As a linear transformation, when you give it x, what it does is it returns to you a vector that's a linear combination of the w's, and the coefficient on WK is sigma k times VK star of x, which is sigma k times this. That's what this means as a linear transformation, right? Again, this takes as input a vector x. You take v star k applied to x, that's this. Then you multiply by sigma k, and you take that to be the coefficient on WK. Okay, proof? Yeah, not so hard. The right-hand side applied to VI, what is that? Is sigma I WI. What is that? That's the same thing as AVI. And that's if I is less than or equal to R, and 0 if I is greater than 1. That is, you want to check that A is equal to this? Well, you know what A is supposed to do to the V's, right? So if you know what A is supposed to do to the V's, just check that this does that. This thing returns AVI if AVI is supposed to be non-zero, and it returns 0 if AVI is supposed to be 0. Therefore, this is A, because we know what it does to the orthonormal basis. Yeah, the proofs are, I want to leave the picture out, but the proofs are short. Let me state the theorem. And this is going to be reduced singular value decomposition, and we'll do singular value decomposition next time. So A has a reduced singular value decomposition. So that's SVD. People will call this an SVD, a reduced SVD. We'll do SVD next time. It's just sort of a non-square version. A, and that's going to be W tilde, sigma tilde, V tilde star with, here are the conditions. You want V tilde star. This is going to be an R by N matrix, and it's going to have orthonormal rows. And the point is that row I is going to be an eigenvector of A star A with eigenvalue sigma I squared, but you want that to be the complex conjugate row. Sigma tilde, that's going to be an R by R matrix, and it's going to be diagonal, and it's going to have sigma 1 through sigma R down the diagonal. Okay? And then you're going to have W tilde, which is going to be an M by R matrix, and it's going to have orthonormal columns. So the picture, these are the orthonormal columns, by the way. The picture is to have a, what did we say? It's an M by N, like this, and it's supposed to equal an M by R, and then an R by R, and then an R by N, right? Like this. So that's which one is which? W tilde, sigma tilde, V tilde star. Right? And this one is just the, the diagonal like this. And the proof is one line. In fact, it's just two words. It's just Schmidt decomposition. If you look at what this formula says, it literally says, so think about what this says, right? This is sigma k, wk, vk star. So this is literally saying you have a matrix whose columns are w1 up through wm. Then you have a matrix that has sigma 1 down through sigma r. And then you have the matrix whose rows are V1 star down through Vn star. I'm sorry, VR star. And you think of this as a block matrix where the blocks have size n by 1. You think this is a block matrix where the blocks have size 1 by n, and then this product is literally equal to that. I mean, it literally is the same thing, right? This is just a way of expressing this product when you think of this as a block matrix and that as a block matrix. There's nothing else going. Okay, so next time we'll do usual singular value decomposition, where that's essentially what you do when you throw in the zeros into the matrix. You put in the zero eigenvalue. It's not anything different.